Welcome everybody to the lecture Semantic Web Technologies. First, let me introduce myself. My name is Harald Sack and I am a senior researcher at the Hasso-Platt Institute here in Potsdam. And my major research topics are semantic web technologies, ontological engineering, information retrieval, and so on. And as you can see, I have written some computer science textbooks related to networking and World Wide Web. And my research group that you can see here, it's called Semantic Technologies Research here at HPI. We are researching semantic technologies and a lot of the stuff that is part of this lecture. So what is this lecture all about? As you can see here, it's all about data, and especially how can we make sense of data if it comes in huge amounts, as for example in the web. So we know that the web is big. It's really big, and you just won't believe how vastly, hugely, mind-bogglingly big it is, according to famous author Douglas Adams. And the problem is that with every minute, the web is getting bigger and bigger. So it's not only the web pages, and it's not only the blog posts and stuff. In future, for example, it will also be things that will be part of the internet. Every device in the household will be part of the internet, will have a web address, and if it comes to an end, each device will put messages on the web and will connect with other things on the web, and it will post also messages in social networks like YouTube, Twitter, Facebook, Google+, or Flickr. And the problem is really now we have huge amounts of data, but how can we then find something on the web? How can we find the small piece of straw in this huge universe of information? To do this, it is very important to make sense out of the information. And as you can see here, if you're not familiar with Chinese language, maybe you don't understand anything. And it's the same for the computer. If the computer sees the information on the web, it has problems to make sense of it, and we have problems to find something. So one of the main problems is, what is the meaning of the information on the web? And this is one of the central questions of the entire lecture. And this is connected, of course, with the concept of semantics. Semantics is nothing else than the meaning that is inside of the information. The word semantics comes from the Greek. Semantikos means it pertains to the character or the study of meaning, and it's part of linguistics, and it's focused on sense and making sense, making meaning of language and symbols. And based on that definition on semantics, we are trying to make this semantics, the meaning of things and of information, explicit in the semantic web. Because if we have access to the meaning of things, then we are able to understand these things. And also the computer will be able to understand it. So, therefore, be prepared. On the semantic web, we are dealing with explicit semantics. Okay, so what is the schedule of the lecture? We have 6 lectures, and we will start first with the web of data, and then we will come in 2 lectures to the semantic web and its basic architecture. When we know the basic architecture of the semantic web, we will come to the question, how can we represent knowledge on the semantic web? And after that, if we have looked at the entire architecture and on the knowledge representation on the semantic web, we will come up with some applications. So what can we do with the stuff we have on the semantic web, and how will the web of data work for us? So let us take a closer look inside the lectures. So the first lecture, the web of data. I will introduce you into the short history of the web. So we will start somewhere in the 60s, and we'll have a look how the web has developed, how has the web become this huge information universe that we are dealing with today. And soon we will discover that, of course, there are limits somehow in the web. You might think that the web might grow bigger and bigger and that there are no limits, but of course, if it comes to the meaning, and if it comes to looking for things, finding things in an efficient way, then of course we will see where are the exact limits of the World Wide Web. And it's here exactly at the limits where the vision of an intelligent web, of the semantic web, really takes place and plays its part. So we will have a look at it. What does it mean if semantics in the web will be made explicit? What can we do with it? How can we benefit from it? And we will have a look at applications in the World Wide Web. So for one thing, for example, we will ask, what is this what you see here? Of course, you will say, hey, it's an apple. But if you know French, this is not an apple. Of course, it's only an image of an apple. So it represents an apple, an object from the real world. But our mind, our brain is capable of talking about things while taking some representator of the thing and not the thing itself. So this is a basic concept of understanding and of linguistics, and also in semantic technologies, we have to look at these concepts. Okay, then we come to the basic architecture of the semantic web. First, of course, we have to talk about how do we identify things. We do this with a so-called uniform resource identifier that you might already know. For example, in your browser, if you try to put a web address in the slot of the browser to access a web page, this web address usually is a uniform resource locator, and the generalized form of that is the uniform resource identifier. Then if we know how we can identify things, we want to represent facts about these things. And this can be done with the so-called resource description framework. The resource description framework enables us to formulate sentences, really simple sentences that represent facts about the world that we want to represent. But it's not only the specialized individual facts. What we have to do is we have to come up with a model of the world we want to represent. So how do we represent a model of the world? And this we can do with a language called RDF schema. So it's Resource Description Framework Schema. It's a schema definition language that enables us to model small worlds with explicit semantics, but only with a small part, a small fraction of semantics. So it's only the first part of the lecture on how to represent things, how to represent knowledge on the semantic web. And of course, if we represent knowledge, we need a way how to access to that knowledge. If we have a large knowledge base of these RDF facts, we need a language that enables us to access these knowledge bases and to do it in an efficient way. And there we learn a language, it's called Sparkle Query Language, and this is kind of a data query language like you might already know from SQL, that is, as it's used in databases. But it's semantic, so it's a little bit different. And of course, if it comes to accessing large quantities of semantic data, we have to think of how we can persistently store this data. And this can be done with specialized RDF databases that are called triple stores. The term triple refers to the structure of these RDF-based databases. These databases contain facts, and these facts are represented as triples in the sense of subject, predicate, object, and to make a small sentence and a small representation of a fact in the world. Okay, so far, so good. The problem now is if we have a knowledge base somewhere in a triple store, represented, that represents a world in RDF, then we have to get it somewhere on the web. So how do we get semantics into the web? And this can be done, for example, with technology called RDFA, which is RDF in attributes, and microdata, which is nothing else but semantic metadata that can be put into the HTML representation of a web page. Up to this point, then we are able to represent shallow semantics, lightweight semantics, in the form of resource description framework facts and resource description framework models in the web. But the world is much more complicated than only simple facts that contain, let's say, subject, predicate, object. There are rules, there are restrictions, there are restraints, constraints and stuff like that, and this has to be represented. And therefore, we have to dive deeper into so-called knowledge representations. So in lecture number 4, we have the first part of knowledge representation, and there we find for the first time the term ontology. And ontology is nothing else but a kind of knowledge representation for computer scientists. But the term has a much longer history. It comes originally from the old Greeks, from the ancient Greeks. And there it's a part of the philosophy of general metaphysics. And we will have a close look on where does this term come from. And in the end, knowledge representation really is a rather old problem. Although the old philosophers tried to understand what's real, what's the essence of the world, how can I describe the world? And this, of course, also means how can I describe knowledge? And this will be subject in this part of the lecture. And of course, it does not only, it is not sufficient if we say we want to represent knowledge in terms of ontology. We need some kind of a formalized language that we are able to process automatically, and that is based on the rules and the laws of mathematics. And then, of course, we come to what we call logic. So the next thing that we have to do is we have to take a close look at the foundations of logic, and we will make a short recall of propositional logic and first-order logic and technologies that we require for the semantic web to work. Because all assumptions that we make, all knowledge will be represented in some kind of logic, simply because of the fact this is a formal language in logic, and there are clear rules and interpretations how logic works. And based on that, what we can do in the end is that we understand the knowledge representation, and understanding means that we are able to deduce or to entail new knowledge that is implicitly hidden in some knowledge base and can make it explicit. So we can deduce new facts. So this is something that is quite extraordinary, and only logic enables us to do that. So propositional logic and first-order logic are well known in mathematics since a longer time, but we will see that these formal languages are not very well suited really to represent the world, because first-order logic is much too complicated and propositional logic is not sufficient enough. So we need something that is in between. And in the 1990s, the artificial intelligence world came up with something that is called description logics. Description logics is a fraction of first-order logic, and with description logics we are able to represent the world, while in the meantime keeping all calculations and computations that are necessary for inference, for proving the correctness and stuff like this, to keep this sufficient or succinct. It means that we can make these computations in efficient time. And description logics, nevertheless, is a formal language, so it's a problem to put description logics directly on the web. For that, we need some kind of a representation language that we also can use and represent as RDF that we already know. And there we will learn the so-called web ontology language that is based on a special kind of description logics. And of course, there might be also situations where this simple description logics is not sufficient really to express facts that are much complicated, to express rules, for example, if-then-based rules. And for that, we need special additional rules for some cases to represent knowledge that we are not able to represent with all the stuff that we had already talked about. So the last part and the most complicated part will be rules in the semantic web. In the end, we will come up with some kind of an architecture, and you see here the Semantic Web Technology stack. And in this Semantic Web Technology stack, all of the technologies we have talked about are represented at a specific layer, and of course you see here the connections to its neighboring layers, and we will very often refer to this technology stack when we talk about the single technology pieces that put together the semantic web technology. So you will see this technology stack rather often. And in the end, in the last lecture, of course, we are putting the question, what can the semantic web be used for? And there, of course, we are talking about applications in the semantic web and in the so-called web of data. And the first thing we are talking about is how can we handle knowledge? How do we design ontologies. How do we connect to different ontologies that might mean the same or might express the same? So this kind of technology is called ontological engineering, and we will talk about ontology design, ontology mapping, ontology alignment. Then we will see, of course, in the world there are no ontologies. Most of the knowledge we have is expressed implicitly in our natural language. So what we are dealing with is text. And somehow we must come up with a way to represent text or to map text to semantic entities. And the process to do this, to come from text to knowledge, is called named entity recognition or named entity mapping. And we will show you some examples how this really works. Then, of course, we will have a look at the semantic web today, which is the so-called linked open data cloud or linked data, which is nothing else but, let's say, a kind of huge distributed database of vocabularies and formally structured data that are represented in terms of RDF, that are interoperable because they are formulated in RDF and they are grounded, mapped, based on ontologies, and they are interlinked. And this is a huge web. Today, this web of data consists of billions of facts, and we will see how to access this web of data and how to build simple applications, so-called mashup applications, that dynamically, from the content of the web of data, create new websites with information that is really nice to have at hand and that would be difficult to achieve in the traditional way, but rather simple if you are using semantic web technologies. And another thing, what can all this be used for? If we refer to the problem that we had right at the beginning of the lecture, it means how do I find things at the internet? How do I find things in the web? Of course, semantics can support traditional information retrieval and can support search engines. And therefore, we will have a closer look at semantic search. We will see that semantic search enables us to more precise and more complete search results compared to traditional information retrieval. And we will give you lots of examples for that. Okay, that's the story so far. In the end, I will give you a few references where you can read all these things we are talking about, and you can look it up in a bibliography. Large parts of the lecture are based on the book from Pascal Hitzler, Markus Krötsch, and Sebastian Rudolph. It's called Foundations of Semantic Web Technologies. So here you can refer to all the basic technologies like RDF, RDF schema, OWL, or description logics. Then for the recapitulation of propositional logic and first-order logic, I would recommend you the book Logic for Computer Scientists from Uwe Schöning. So especially for computer scientists who are interested in logic and do not want to deal with the, let's say, sometimes complicated frameworks that mathematicians have developed, then this is a rather nice book to understand the basic concepts of propositional and first-order logic. And then, in the end, if you want to have a closer look on linked data and the linked data principle, so what is today the semantic web, then you can look it up in the book from Tom Heath and Chris Bitzer, Linked Data, Evolving the Web into a Global Data Space. And in the end, during the lecture, we will give you further remarks on bibliography and things that are worthwhile reading and bookmarks and stuff like that. And these bookmarks you can look up at our Bibsonomy page. You will see the URL there on the webpage of the openHPI. Okay, so to wrap it up, this is the course of the lecture Semantic Web Technologies, and I hope to see you again. Thank you very much.